Start recording. Alright, can you see my screen? Sam?
Yes, sir.
Okay, cool. So the last thing that we talked about on here was we finished with pointers in C. So now I wanted to go into something a little bit more complicated, which is function pointers. So as we talked about before, in C you have functions, and that helps you modularize your code. So like we had before, we had pointers for variables. We can also have pointers for functions. So here we have a function called print stuff. Let's look at that one. Let's focus on that one first. So if we just call print stuff, and then we run our code, we will see it says hello everybody. So what if I wanted to sort of save this function into a variable? So what I could do is make something called a function pointer, which has this weird syntax. So as you can see, I have a void pointer, my function pointer, which takes in a void. So basically what I'm doing here is I'm copying the return type and any parameters that this function takes in, and I'm using the pointer notation like before. So if instead print stuff took in an int, so if it took in an int here, we could change this to an int. And that would be how you declare a function pointer out of print stuff. So let's go back to void. And then, so now that we have the function pointer saved, let's just take a look and make sure that it is indeed that. So let's print the actual pointer value of my function pointer. So if we print that out, then we can see that we have a hex number, hex 7F634, blah blah blah. So that's the memory address where this function pointer points to. So functions are stored in memory somewhere because the instructions inside of the function need to be put somewhere so that when we want to run the function, we go there and then run the function. So this 7F6342 blah 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 is where this instruction is stored for printf. So how would we call this function? So what we would do is we just use my function pointer as if it was the name of the function. So we just use the parentheses as you would normally call a function. So if you do this and we run it, you can see that it prints hello everybody. That's just the same thing that we would do by just typing print stuff, the parentheses. And as you see here, in order to get the pointer, the address of print stuff, we just put its name there. We don't have any parentheses. We don't need the ampersand, but it would still work, as you can see. So it's the same thing. So this is equivalent to this. So usually people just do it like that. And you can call my function pointer with just the parentheses, or I'm also pretty sure you can dereference it like a normal pointer and then use parentheses. And yeah, that also works. But you don't need to, and there's really it's standard not to do that. So why would we use a function pointer? So in general, you'd use a function pointer for something like a callback. That's probably the most common use case for function pointers. So what would a callback be? A callback is a function you'd call when something completes. So say you're working with the microcontroller and you just received data from you just received some UART data and you want to process it. So when you're setting up the UART, which you'll learn about this later, just say you receive some data from somebody, and as soon as that happens, when you're setting up the receive function for receiving the data, maybe you'd pass in a function and it would save that function somewhere so that when it receives data, it calls that function and passes in the data to that function so you can do some special processing on that data that you might want to do. So I have an example here of how that might work. So I have two functions here, add stuff and multiply stuff, which both take in two parameters, variable 1 and 2, and they return the sum or the product of the two numbers. So let's just give an example of how add stuff works. Let's store the result in an integer. Let's pass in 1 and 20. And then print the result. The result is okay. As you can see, the result of adding 20 and 1 is 21. We can also do this function pointer style. So if we see how this is set up, it's returning an int and it's taking in two ints. So we'd make a function pointer in this style. It's an add function pointer, we'll say, and it takes in two ints. Equals add stuff. So then we can just say result. Move that down here. Instead of add stuff 1 and 20, it can be add function pointer 1 and 20. Now we can run that. Bam, it's 21. And we have a multiply thing that does the same exact thing. So let's see how we can pass in this function pointer to another function that might use that function pointer. So right now we have another function called do something that returns nothing, and it takes in a function pointer that returns an int and takes in two ints. So we have two functions that satisfy that form, this add stuff function and this multiply stuff function. So we can pass in pointers to either of these two functions and it would use them in some way. So let's see, what does do something do? So it takes in this function pointer and it has two variables, variable 1 and variable 2 was 23 and 45. Let's make that 4 or something, actually. So we're printing, now doing something with %d and %d, variable 1 and variable 2. So it's going to say now doing something with 23 and 4, and it's going to print the result is, and it uses that function pointer on these two variables. So this is how you can make sort of like a dynamic function. This function can do multiple things. It's based on what this function pointer does. So if we passed in add stuff to it, it would print that the result is the addition of the two. If we passed in multiply stuff, it would print the result is the multiplication of the two. So let's test that out. So if we call do something on, and like we said before, since a function pointer is just the name of the function without any parentheses, we can just pass in the name of add stuff. And that would be the same as passing in a function, and that's just passing in a function pointer to add stuff. So if we run this, It says now doing something with 23 and 4, and it says the result is 27. If we instead change this to multiply stuff, and again, you see we don't pass parentheses after this. We don't do a function call. We're just passing in the name. When we run this, it says now doing something with 23 and 4, the result is 92. So that's the same as just 4 times 23. So that's a really cool way to make a function that can do multiple things based on whichever function pointer you pass in. And how a callback would be used is, like, say you have set up something. Okay, so here I'll throw some pseudocode in here. So say you have a thing called set up something, and you have a global variable int global var. You have a global function pointer. So you have something like this. Global var. Okay. Cool. Okay. So say this is your global variable. And in your setup function, you'd store this global variable equals function pointer. And then say you have another method. So this is your just received something method or function. So say when you just receive something, maybe you wanna, and that those things you received are data 1 and data 2. You just received 2 bytes of data, and you want to process them. So you pass them into your now saved global variable. So that's how a callback would work. So in your setup function, you save your callback function. So that's our callback function, which is our global variable. And then when you say just receive something, so you just receive some data, two things of data, and then you use your callback function, which you saved from before, to process those 2 bytes of data. And as we've seen before, this can be used to pass in a wide variety of functions to do different things based on the situation. Like before, we passed in an add, or we could have passed in a multiply. It all depends on the context of the system. So that's pretty much all the pointer stuff I wanted to talk about. So let's talk about some others.
I have a question.
What's up?
What if you have a variable with the same name? Like as a function?
The same name as a function?
Yeah. So say you had like a multiply stuff variable.
Okay, let's test it out. So say you had a multiply stuff variable, and you also have, so are you talking about like this situation? You had a variable called multiply stuff and a function called multiply stuff? Well, you know the difference between the two, because one of them you can only call by using parentheses, and the other one you can only do assignments with.
Well, so like, what if you pass it as a parameter? Does the variable take precedent, or does the function?
Let's test that out. So we pass in multiply stuff to do something. So as you can see, we get a warning that says passing argument of 1 makes pointer from integer without a cast. So it seems that it is it's using this multiply stuff variable because it says that it's attempting to cast this int to a pointer. So that's mostly due to the fact that this is within, I guess, a more local scope than this function. And yeah, that's pretty much it. So some other C stuff that I wanted to go over was scope and qualifiers. So if we just delete all this. Okay, so let's go over scope first. So say you have a variable called myvar. Okay, and then you have these curly braces here, and you can do that in C is just have curly braces with nothing attached to them. And then we try to print an integer. Then this should give me either a warning or an error. It doesn't. Okay. I guess it depends on the compiler. Let's put this inside a for loop instead. So, what? Oh, I'm being stupid, actually. My bad. Okay. So say you have, I did the wrong way, the opposite way. Okay. Say you have my variable inside these curly braces, and then you tried to print it outside of those curly braces. As you can see, my linter is already giving me an error that is undefined. So as you can see, when we try to compile it, it says my variable is undeclared, first use in this function. That's because when we created this variable, we created it here inside these curly braces. So these curly braces, whenever you see curly braces, that's a form, that's a type of scope. So scope is like how you can see, if you can see that variable or function or not. So when you're in the int main function, you're in this scope here, which is the function scope for this function, for this main function. So anything in this scope or deeper can, so if we make a function here, a variable here, function scope variable equals 23, and then we said my variable equals my function equals function scope variable times 2 or something, and I wanted to print my variable. Let me comment this stuff out right now. And you can see it prints 46 right here. That's because this is in the scope of main, and then this is a new scope, so it's a deeper scope. So anything in a deeper scope can see anything from a less deep scope. So we can see this function scope variable, and we can also see any new variables. So this my variable was made in this scope, so when we try to print it, we can access it. the reason this was giving errors was because my variable was created within a scope that is deeper than the current scope, and we can't see variables or functions that are created in a scope deeper than the scope we're in right now. So that's how that works. And how this also ties into something else is something called global variables. So global variables are made at the file scope. So that right here, this is function scope because it's declared within a function. If we made some, we can also make a variable outside here. So if we make global variables, we can make integer global scope variable equals 11. And then we can say our function scope variable is 3 times our global scope variable. And let's just delete this for now. And then we print our function scope variable. We can see since this is less deep than this function scope variable, so that means that we can see this global scope variable. It's the global scope variable is something that is the least deep, in terms of scope. So anything can see this global scope variable. So if we just run this, we see we print 33. But not only can this main function see this global scope variable, also this function here, he can also see this global scope variable. So if we print hello everybody and a colon, and then we print the integer, and then we're going to print the global scope variable, and we call print stuff. You can see that it says hello everybody 11. So this function can see this global variable. So you may think, what's the point of having functions? What's the point of passing in anything to functions when we can just make everything global variables? So like, for instance, I can have add stuff, 3, 5, or let's have two variables here. In my var1, my var2, and my var1 equals 3, my var equals 4. And then we could just pass in those two variables to this add stuff function. I run that. Let's print what this is. Result is %g. It says result is set. So we added these two. But you may be thinking, what's the point of even passing anything in here when we could just make these two global variables? Let's make another function called in adding things. Takes in nothing. Return. Here, hold on. Let me put this back here. So in global var1 equals 3, global var2 equals 4. And you're seeing different ways you can create variables on one line or multiple lines. And we're returning global var1 plus global var2. And then we could print, let's call this one the local result. And then this is the global result. not going to use the add stuff that takes in values anymore. We're just going to use the adding things function. And let's run this. It says the local result is 7 and the global result is 7. So for this add stuff, we needed to take in 2 variables. And we took in 2 local variables. But for our other function, we just return global variable 1 plus global variable 2. So what's the point of passing anything in when you could just access everything as a global variable? So the reason we do that, the reason we make functions like this add stuff function instead of this adding things function is because we want our code to be modular. So we want to be able to say I'm working on a new project now, and I want to use stuff from my old project. So you wouldn't do this for something as simple as just adding 2 numbers, but let's say we were, and we're like, oh, I want to reuse my code. I want to reuse my my add stuff function. So which one of these would you be more likely to reuse? You'd definitely be more likely to reuse this one, this add stuff function, versus this adding things function. Because this adding things function requires your variables to be named certain things, and it requires you to have global variables in the first place. Global variables are a bad practice, as stated by most people, in most cases, not all cases. Like a lot of embedded stuff requires global variables. So this doesn't apply as much to you guys, but when you can, try to make local variables, because this makes it so that we don't access variables unless we need them. So you don't have something called I don't know. I think it would be called something like namespace clashing or something. I don't know. But you don't have like access to these variables when you don't need them. Like this add stuff function only needs these 2 variables passed in. It doesn't need 2 global variables. And also, if we're taking in global variables, we're just restricting ourselves to what we can take in. So, anyways, try to use local variables whenever you can. And let's go over one more thing with regards to scope. Oh, and if I hadn't made it clear before, whenever you see curly braces, that means you're entering a new level of scope. So you can use these curly braces by themselves, or you can use them, or as you know, you need to use them whenever you use, well, you don't need to, but whenever you use multi-line if statements, or while loops, or for loops, you use curly braces. And so that puts you in a deeper level of scope. So that's something that you need to keep in mind. So that if you say you're in a while loop here, and you make a variable in here, and then when the while loop's done, you want to access that variable, you won't be able to, unless what you do is you make the variable outside the while loop, and then you do stuff with that in here. Then, since when it was created, it was made at the function scope of main, and you would be able to still access it here outside of the while loop. Okay, and as Sam brought up before about wondering about what would be used when you had a variable and a function with the same name. So what if you had 2 variables with the same name, but one of them was a global variable and one of them was a local variable? And what I mean by local variable is something made at the function scope. So say we had something called my variable 42 42 equals 3, and that's our only global variable. And then we also made that same variable, a variable with that same name, and set it equals 7. And then we wanted to print out what that variable is. So what is my var 42 going to be? So let's think. So my var 42. So when we're looking at this right now, it could either be this one or it could be this one. Because this is a global scope, we can access it from anywhere, and this is a local scope, and we're at that same scope level right now. It could also be this one. So if we run this, we can see that my var 42 is 7. So how C works is that it will always access the most local scope that it can variable. So this global scope is the most breadth-y scope, I guess, whereas this is more local. And that also applies to something if you're in a for loop. Yeah. And you wanted to print what my var 42 is. So my var 42, it could either be this one or this one. This one isn't at the same scope level as what we're trying to access it at now. But since it's the closest scope level, it's just one more breadthy, I guess. And this is two out. It will use this one. So if we run this, see it prints it 5 times. My var 42 is 7. So that's all the scope stuff I want to talk about. So now on to qualifiers in C. So if you saw what I was doing before, if you saw that before I made a variable and I put the word const in front, so I can have something constant my var equals my const var. So, yeah, equals 33. If we print it, you can print it just like a normal integer. My const var, and boom, it prints 33. But this const is something in addition to it being an integer, even though it's also in front of the name. So const means that this variable can't be changed. So say we try to do something like my const var equals 12 now. As you can see, my lecture is already giving me an error that this expression must be a modifiable L value. So if we try to run it, we get an error, and it says assignment of read-only variable my const var. You want to use const whenever you can, because this will give you more information, or someone else who's reading your code more information about this variable, that this shouldn't be changed ever. And you can also specify const when you're taking in parameters or functions. So like I could put const in front of this right here, and that lets you know that you're taking in a constant value. You can, okay, so then there's some more, there's some other qualifiers. So qualifier is what this const is. It's something that's put in front of the variable name in addition to the data type. You can also put const So you can put that pretty much anywhere you would put a data type. So you could return a constant int, which is something you won't be able to change. So there's some other qualifiers. One of them is going to be static. Another is volatile. We have extern and inline. So let's go over static first. So static is generally used in front of functions. Static int adding things. So this static keyword means that this function is it's defined here and only accessible here. So it's basically making this function a private function to this scope, which is this file. So in C, you generally have multiple files for each of your projects. So each of the files can access variables from other files. So let's go into let's go like this. Yes. C file dot C and C file dot H. So our C file dot H is called a header file, and these .c files are called source files. So a header file can have our adding. Let's put our multiply function in there. So our header file has to have something called a header guard, which protects against this file being included more than once. And this is the normal syntax for header guard. Usually put the name of the file and then underscore h underscore. And then you can put the name. Then you normally put all the prototypes in the header file and all the definitions in the source file. So like we used include before to include stdio.h to get stuff like printf, we can include our own files using the quotes instead of the these things. Wow. Okay. So we're including cfile.h, so that gives us access. So what an include does, it's basically, you can think of it as I copied everything in this file and put it right where this is. So this can now see this multiply stuff. So we are going to make the definition for multiply stuff in here. So now we have a header and definition. So let's remove that from here, which we did. Let's get all this other stuff real quick. Okay, and now we can include our header file. You want to include header files and not source files, because that's the standard for how C should be used. So, like I said before, an include is just a copy and paste. So that means we can see, basically, it's just like copying that, pasting it there. So that's our function prototype that we see. So now we can use that. We can use this function, multiply stuff, on say 3 and 5. And we want to print this out. The result is boom. now if we okay, so how we've been using our compiler before is we've just been compiling main.c. But now, since we have other source files that have function definitions, we need to also compile those. So if we go here, this is where we put all the functions or all the files that we want to compile from. So now if we do that and run it, we get the result is 15, which is just multiplying 3 and 5. And that multiply function is done in this file. Say we used our old compile command, and we're just compiling main.c. We get an error. In function main, undefined reference to multiply stuff. Collect to error LD returned 1 to exit status. So what LD is, that's the linker. So when we include this, this function prototype is telling us that this function exists, it's just defined elsewhere. So whenever we get an undefined reference, that's a linker error. So what that means is that the linker isn't getting the definition. It's not able to. It knows that this function exists, but it doesn't have like the actual source code inside that file because we're not compiling this C file.c. So it never sees this stuff. So that's why we need to compile both in order for it to link the two translation units together. So a translation unit is basically a compiled version of the file. It compiles each file separately and then links the into translation units, and then it links the two together. So any definitions that this guy was expecting is now provided by the linker, linking this into there. And that's not too important to know. Just know that if you see an undefined reference, that's a linker error, and that's even further supported by if you see the words LD or the word LD. So that's telling you something that maybe one of your files isn't getting compiled by the compiler, or maybe you didn't define it at all. So if I deleted all this, and then we try to compile, you get another linker error. Okay. So let's go on to these as static. So this is what we would call a public function. So we might also have a private function. Private. There, let's just put it down here. Let's put it here. Private functions. Public functions. To multiply. So say we had a function that multiply stuff is gonna call, and that function would actually do the multiplication. Okay, so now let's run our code and we get the result is 15. We're just abstracting away the multiplication to one function deeper. And you would never do this, it's just for, it just helps me show you guys this concept. So right now we have this do the multiply function. Why not just call that directly? So let's do that. Would this work? Let's make sure. Shoot. Okay, so we got the exact name. You run it. The compiler says implicit declaration of function do the multiply. That's because in our header file, we never have a prototype for do the multiply. So we're basically calling this function without even knowing it exists. So if we run it, it still works, but that's compiler dependent. You never want to do that. You would want to have this function in your header file. But the thing is, that function is supposed to be a private function, but we just called it. So what I mean by private function is that only things in this file should be able to see it. So we only want the multiply stuff function to be able to do the multiply. So we can get over this implicit declaration error warning by declaring do the multiply ourselves. And then this uses another one of our keywords. So this uses extern. So extern is what is implicitly placed in front of every function declaration. So extern, this is equivalent to extern. It's always there by default. So extern is telling us that this function or variable is defined elsewhere. So if we try to compile this now, we don't get this error before because we told ourselves that, yeah, this is defined elsewhere. So we were just able to call do the multiply by saying, without any warnings or errors, by saying that it was declared elsewhere ourselves in our own file. We don't want anyone besides stuff in this file to be able to use do the multiply. So what can we do to circumvent that is to use this keyword / qualifier static. So if we now compile, then we see that we got a linker error, undefined reference to do the multiply. That means that, like I told you before, we're not getting this code. This code isn't showing up, but we are compiling cfile.c. So why isn't it showing up? It's because of the word static. Static is making it so that this function can only be seen in this translation unit. And when I said before, translation units were just files being compiled and any header files they include. So each .c file is its own translation unit, usually, in like 99% of cases. So that means only stuff inside of this C file.c translation unit can do the multiply. So if we call multiply stuff, which is what we're trying to call anyway, which is what this is enforcing. It's enforcing that multiply stuff is a public function. That's what everybody else sees. So every other file sees multiply stuff. That's what's in our header file. And then only stuff in this file can do the multiply. So if we call multiply stuff now, see we don't get any warnings or errors, and we get the results 15. So it works. It works that's how static works, as being able to make things private. And this private public use of static and extern doesn't only work for functions, it also works for file or variables as well. So you can also have a global variable here. My global variable. And I said before that functions implicitly have extern placed in front of them. Variables do not, so we want to put this extern here. to tell the compiler that this variable is defined elsewhere. And then we want to put the definition here. Variables. And then we can access that variable. So from main.c, when we include cfile.h, we see, oh, it has a global variable called my-global variable that's defined elsewhere. So that's defined in the cfile.c. So if we print that, let's get rid of this, see what you get. And you see the result is 4. So we printed my global variable, and it has been assigned 4 here. What if we didn't have extern? So this is where it gets kind of confusing. So now every source file, every translation unit that includes this cfile.h, it no longer has extern in front. So that means that when it's actually, this variable is created. So when we